Hello everyone, this is Bhumika Mohan. In this video, I am going to talk about a topic related to theory of computation, that is optimizing succinct representations of finite automata. The contents of this video are: first, I'm going to give an abstract of this video, then introduction, literature review, methodology used, and the outcomes of this paper, and in the last, its conclusion. So, coming to the abstract, this paper explores the construction of succinct representations for deterministic and non-deterministic finite automata, that is, DFA and NFA. It presents efficient methods for minimizing the state space and transitions while preserving language recognition capabilities. For DFAs, we employ state minimization techniques, while for NFAs, we focus on reducing non-determinism by transforming and optimizing transition structures. The analysis highlights trade-offs between state complexity and expressiveness, offering practical approaches for applications requiring compact automata representation, such as pattern matching and formal language processing. We also address the computational complexity of transforming NFAs into DFAs, emphasizing the impact on space and time efficiency. Coming to introduction, the finite automata, both deterministic, that is DFA, and non-deterministic, that is NFA, are fundamental computational models used in various domains, including language recognition, pattern matching, and compiler design. Although the former is directly unique, its much more flexible variation is an NFA, which allows multiple transitions from the same state and input. However, this often leads to the need for a greater number of states and transitions so that it is relatively less efficient in both storage and processing. The concept of succinct representation attempts to alleviate these inefficiencies by reducing state space and improving transition structures in both NFAs and DFAs without losing the language accepted. States minimization for a DFA is very well explored with assurances that it is possible to get a smallest equivalent over a given language for a given language. State minimization for an NFA, however, results in higher complexity when reducing inherent non-determinism again. Transformations are more complex within the automation, which affects its size and computation efficiency. This paper aims to design and analyze diverse techniques for constructing more compact representations of DFAs and NFAs, balancing the trade-offs between expressiveness and space efficiency. Our approach focuses on both theoretical insights and practical applications aimed at offering tools for creating efficient automata representations, highly relevant informal verification, text search applications, and artificial intelligence techniques. A DFA, that is D, is a quintuple D equals sigma, Q, Q naught, delta, and F, where sigma is an alphabet, a finite set of letters, Q is a finite set of states, Q naught belongs to Q, which is the initial state, delta is Q into sigma, that is Q, is the transition function, and F is a subset of Q, is a set of final states. Here is an example which tells the state transition diagram for a DFA-D, where D equals sigma, Q, Q naught, delta, and F, such that the first one is sigma, where it is 0, 1, which is the input symbols. Second one is Q equals Q naught, Q1, which is the finite set of states. Q naught equals Q naught, marked with an incoming arrow coming from nowhere, is the starting state. F equals Q naught, and the transition function is defined as the following set: transition Q naught comma 1 equals Q naught, delta Q naught comma 0 equals Q1, delta Q1 comma 1 equals Q1, delta Q1 comma 0 equals Q naught. Precisely, the DFND accepts all the strings containing an even number of zeros over the binary alphabet. Coming to the literature review, one of the best established studies in the area of formal language theory and automata theory is the study of finite automata, both deterministic, that is DFA, and non-deterministic, that is NFA. It is known that Hopcroft's algorithm for minimizing DFAs is the most efficient known one to date, having polynomial complexity while not losing recognition of the language. This work serves as a basis for practical DFA minimization in any kind of application related to compiler optimization and text processing. Things become more complicated in the case of NFEs. The subset construction algorithm can also be used to determinize an NFA, although its use generally leads to an exponential blow-up in the number of states, a phenomenon that is known as the state explosion problem. How to represent efficiently NFAs without losing their expressive power remains an important open problem that has motivated much research. The seminal work by Aho, Hopcroft, and Ullman, one on automata theory, studied natural trade-offs between the compact structure of NFAs and the deterministic efficiency of DFAs. More recent work discusses algorithms for non-determinism reduction in NFAs, techniques of partial determinization which try to optimize NFAs without fully converting them to DFAs. To deal with the size and complexity that large-scale automata present, compressed representations of automata, including BDDs and symbolic automata, have been developed. These allow states and transitions to be manipulated more efficiently but raise questions of computational overhead and practical implementation. To briefly summarize, such existing work lights up well established methods in DFA minimization and gives an indication of the continuing challenges in the conscience representation of NFAs. This paper continues on those foundations and outlines new techniques for reducing the size and complexity of automata, with an emphasis on the theoretical and practical applied desire for space efficient representations. Coming to the research methodology used in this paper, the study employs a combination of theoretical analysis and the algorithmic development to achieve succinct representations for deterministic and non-deterministic finite automata, that is DFA and NFA. The research is divided into two main phases, DFA state minimization and NFA optimization. The first one is DFA minimization, where we will use the state minimization algorithm by Hopcroft, as this would transform the given DFA into its minimal equivalent through state merging of indistinguishable states. The strategy targets achieving the best possible outcome in terms of reduction in the number of states, such that the minimized DFA accepts the same language as the original. The second one is NFA optimization, where the partial determinization and optimization of the transition structures of NSAs is the research in the reduction of the size of the automation without complete conversion to a DFA. The research discusses the algorithms that reduce non-determinism based on the increase in states as well as transitions and compares various techniques in finding the optimal method that satisfies the balance between size and complexity. Complexity analysis. The work carries out an exhaustive complexity analysis where we compare the time and space efficiency of minimized DFAs and optimized NFAs. We talk about the trade-offs between state reduction and computational overhead, oriented with managing exponential state growth, which is typically associated with the determinization of NFA. Experimental validation. The methods proposed are tested using a set of benchmark automata that includes random generated automata as well as instances from real-world formal language processing. For each method, their performances in terms of reduction in the number of states, transitions, and overall computational efficiency were compared. Through this methodology, the research aims to provide practical and scalable techniques for constructing succinct representations of both DFS and NFS. The outcomes of this paper is the results of the study demonstrate significant improvements in the succinct representation of both deterministic, that is DFA, and non-deterministic finite automata, that is NFA. For DFAs, applying Hopcroft's minimization algorithm yielded optimal state reductions, with minimized DFAs maintaining language equivalence while reducing state space by up to 50% in most test cases. This confirms the effectiveness of well-established minimization techniques for deterministic automata. For NFAs, the partial determinization and transition optimization methods successfully reduce the complexity without fully converting the NFAs to DFAs. The experimental results show that, on average, state space and transition complexity were reduced by to 40% depending on the structure of the original NFA. However, the state explosion problem remains evident when complete determinization is applied, validating the need for partial or hybrid approaches. Complexity analysis revealed that DFA minimization maintains polynomial time efficiency, while NFA optimizations, though more complex, remain computationally feasible within practical limits for large automata. Experimental validation on both synthetic and real world automata demonstrated the scalability and robustness of the proposed methods, showing substantial improvements in space efficiency and processing speed. In conclusion, the results confirm that the proposed techniques effectively balance space optimization and computational efficiency, offering practical solutions for applications requiring compact automata representation. Coming to the conclusion, this paper presents effective methodologies towards succinct representation of both deterministic, that is DFA, and non-deterministic finite automata, that is NFA, that would result in a considerable dimension of state space reduction with transition optimization. In the DFA, established minimization technique like Hopcroft's algorithm, which was very efficient to produce minimal automata while preserving language recognition. In the case of NFAs, partial determinization and transition structure optimization offered significant reductions in complexity and followed up without fully converting to DFAs, thereby avoiding the state explosion problem. The research indicates that even though the minimization of DFA is well known and efficient, it is more sensitive for the optimization of an NFA. It needs better balance between expressiveness and efficiency. These techniques open routes to practicable and scalable solutions for various domains such as formal verification, pattern matching, and language processing. Further studies of hybrid techniques and real world applications of such succinct representations within large scale systems are topics of further study. Thank you.